The next example, a uniform rigid bar of weight W is supported in a horizontal orientation as shown by a rope that makes a 30-degree angle with the horizontal. The force exerted on the bar at point O, where it's pivoted, that's our axis of rotation, is best represented by a vector whose direction is which of the following. So we're trying to identify kind of what force is being exerted on the bar at point O here, so that our bar is supported, it's in the static equilibrium situation. So first thing we want to do is let's go through and identify the forces acting on the bar. First of all, it tells us the bar has a weight. So we know we have weight acting down. Now, this whole bar has mass. The mass is distributed evenly, right? It says it's uniform. So where the weight is going to be acting on the bar will be at the center of mass. And so since it's uniform, that'll be half the distance of the bar. So the weight will be acting at half the length here. We'll have that force of gravity or the weight. I guess I'll use the same notation they did in the problem. Right. The next known force that we can identify is we're going to have tension through the rope. And so tension's always directed along the rope. And we do see that it's at an angle, which means there is an x component pointing to the left, ftx, and a y component pointing straight up. Let me make that a little better. Fty. All right, so just with what we know about forces, right now we see we have a component pointing to the left. So we have a force pointing left, and we don't have any forces pointing right, which means that as it's shown, this would have acceleration to the left. But that's not the case we want. We don't want any acceleration here. And so we automatically know we have to have at least something pointing to the right to balance out that ftx. All right. Next, I want to get into a little preview of static equilibrium, not really looking at it as a calculation, more just conceptually. So we already mentioned we need our net force to be 0 so that we have no linear acceleration. But if we're dealing with true static equilibrium, that means it's not rotating either. So that means we also need the net torque to be 0, so we don't have angular acceleration. And so let's imagine for the net torque to be 0, it should be 0 at any point along this rod. So let's move our pivot point to the weight, where the weight is acting at half of the rod right here. If we do that, we see that on this right-hand side, we have Fty up, which would cause our rod to start rotating counterclockwise. But again, we don't want it to rotate. We need it to be in rotational equilibrium. We need the net torque to be 0. And so that means we need some kind of force that would cause a torque to be clockwise to cancel that out. And so the way we'd get that is if there is some upward force over here at point 0 as well. And so we've identified, well, we need a force pointing to the right to balance Ftx. And for rotational equilibrium, we need a force pointing up to balance Fty. And so that means B is going to be the best representation of the vector at O.